Hey everybody, it's Ripley back again. We're going to talk about functions of multivariables. I love this section. It's such a fun section because it's such sort of a logical extension to what we've done in planar function theory, like on the Cartesian plane. Okay, let's go super slow. Well, let's remember stuff. So let's say that I have y equals 5x squared plus 1. Hopefully you can visualize that relatively easy. Remember that this is written as f of x. This has a domain. What's the domain? The domain is all reals. It's from negative infinity to infinity. And that this comes from the reals. Remember, we could write this as the reals. In fact, it's all reals. If I had y equals f of x equals 5 root x plus 1, hopefully you can see that as well, then the domain would be everything from 0 to infinity inclusive. Here we could say this is it's a subset of the reals, right? Does that make sense? So what we do with a function of multiple variables is hopefully predictably what you can see is instead of just having an x as an independent variable, we have a point as an independent variable. So now rather than if I graph this guy right here, 5x, I'm going to move it up, it looks something like this. I know that this guy looks like this, right? Ooh, that's pretty good. I grab a value from the domain and I go up to the curve. Inversely, if I grab a point from the curve, I can plot that down onto the x-axis to figure out which x-axis produces that. If I'm trying to figure out if I can grab a point over here, it doesn't work because there's no function over here. On this function, 5x squared plus 1, well, you can probably see that I could grab any value on the curve and get back to the x value that produced it. Now, that said, when I deal with a function of x, y, I'm no longer on a plane. So what I want to do is, first and foremost, I want to sort of sketch you something that might look like a function of both x and y. All right? So again, hopefully not too terribly. Now this becomes really important. This guy's x, this guy's y, and this guy's z. And then let's just make something goofy up here. I'm going to make this, let's make a hemisphere floating up here like a disembodied head. All right? Oh, hemisphere, nasty. All right. Ooh, that's a terrible looking hemisphere, but hopefully you can kind of see what's going on, right? This is the bottom of the hemisphere and up it comes. Well, what's going on down here in the xy plane? Very much like, remember, we grabbed a point here and we drug it down to the x-axis, and that was the corresponding x value. Well, we have a set of points now. All right, so this guy lives in in R3, right? He's three-dimensional. That's what that means. Now, what's going to happen down in the xy plane? Well, let's just look at it. Ooh, pretty lavender. What I'm going to have is I'm going to have a circular kind of shadow. The best way to think about this is a shadow. If I had a light, shining down, what would it do on the xy plane? Well, it would give me this. Now this region is called the domain region. This is the domain. And the domain, rather than being an individual point on the real number line, the domain is a set of points, right? It's the set of all x, y in R2. And for lack of a better term, I'm going to say that work. In other words, very much like -1 wouldn't work, quote unquote, in this function. Any value outside of here, if this is the sum total of our region in R3, then these aren't going to work, so to speak. But all of these points, let's do this. This point's going to work, and it's got an x. Let's call x1, y1. And this point over here is going to map. Now by work, let's make sure we understand what that does. That's going to map up to a value on our hemisphere. This guy's going to map up to our value on our hemisphere. And we can actually, this is going to be x2, y2, we can actually write it in sort of a standard issue notation. But we don't, because it's awful. This value would be, what would it be? Well, it'd be a z value. And z would equal f of x2, y2, instead of just an f of x, an f of x. Now, let's think about something else. Another thing to think about is, and this is based on what I just said, if y equals f of x, then doesn't z have to equal f of xy? Because the ordered triplet, right? This guy right here is going to have an ordered triplet, which would be, what would it be? It'd be x2, y2, and then f of x2, y2, right? Now we don't necessarily want to say z2 because that could be confusing. Even though, I reckon we could say z2, but I like to leave it in more of a formal. Let's keep some semblance of mathematical decorum here and leave it in the formal notation of f of x2, y2. We should see that comfortably as a point in space. It has an x value, it has an x value that goes this way, a y value that goes this way, and then whoop, up we go onto the hemisphere. Okay? All right, so cool. Now, excuse me, we understand how that guy works. So we can do this algebraically, just like we used to fight with domains and ranges and all that good stuff back in the Cartesian plane. What if I just simply call this x squared plus y squared equals f of xy, which remember equals z, which equals z. I'm having a heck of a time, aren't I? Equals z. So another way to think about this is this would be z squared equals x squared plus y squared, but with a caveat. Remember, this guy is only going to spit out positive numbers. I'm only going to get positive values out of this. I can't get negative values out of that. So while z squared, I can stick negative values of z into this, that's not going to work because since z equals root x squared plus y squared, z is only going to be positive. It's akin to, remember when we did y equal the square root of 1 minus x squared, which was the top half of a circle of radius 1? Right? Because I'm only taking principal square roots. It works exactly the same way. Otherwise, what happens, like with regular functions, is down here, below here, I would get another hemisphere. I guess technically it's not a hemisphere, it's just sort of the top, it's the surface area of the hemisphere. That's a better way. And then I've lost my quote-unquote functionality. Now, I'm going to give you the formal definition of a function of multiple variables, okay? So we are officially in multivariable calculus, which is kind of exciting, multiple variables. All right, here's the formal. This is a robust, rigorous definition. It says if f is a function, whoops, wow, Ripley, less caffeine, man, is a function of two variables, two vars. I'm going to be a little lazy. With domain D. Now remember, this guy right here, this purple guy right here, is our domain. It's the shadow. It's the shadow that the figure itself casts onto the xy plane, and that's going to be important, okay? With domain D, then the graph of f is a set of points x, y, z. Now they're points, not vectors. Okay, we're dealing with points now. You got to shift your head a little bit. We're away from vectors for a little bit. We'll be back to them, but I want to make sure that you understand that we're away from vectors right now. And this guy these points live in R3. We're not afraid of that notation, right? It just means it lives in three-dimensional space, such that z equals f of xy and xy is an element of the domain, which is also, you can tell what we're looking at, is an element of R2. I added that. I just want to make sure that we understand, very much like if you recall the footprint problems from Calc 2, this is similar. We're not building them at all the same way, but it's akin to it insofar as this figure, this set of points that we're calling f of xy, casts a shadow down onto the xy plane. We grab a point, we map it up, we get the graph, but the domain is the set of points in the xy or the Cartesian plane that produces values in our function. All right, so let's deal with one where we run into trouble, but let's keep it super simple. Let's say that z, remember, which can be written as f of xy, all right, that is, whoops, see, I get in the habit of vectors, is equal to x squared plus y cubed over x squared. All right, now what's the domain of this thing? Now remember, it's the set of all points x, y. So the domain is going, how are we going to write this thing? It's going to be the set of all points x comma y such that what? Well, I have no problem in the numerator, right? This thing can get as crazy in either direction as it absolutely wants to, and then bah, I got troubles with the denominator, right? So I would say such that x cannot be 0, and I'm done. Now, we're going to deal with far more complicated problems with this, or than this, but it's good to be able to just sort of take it easy in the beginning. It works the same way as it did in 2-space, except I have to be able to sort of see what's going on with 2 variables at once. For example, had I thrown a y in there, all right, now I have to say D is the set of all points x comma y such that x not equal to 0 and y not equal to 0. So writing in this mathematical notation is really, really important too. And those of you that struggle with that might have some difficulty with some of this. Okay, so I want to graph this thing. I want to show you what this thing looks like because it's awesome. And we'll see if the grapher, even if this is such a blip at x equals 0, I'm going to do the original black one. I'm going to do the original black one so we'll just take a gander at that. And we're going to be able to use graphers. I love graphers. So, whoa, what's going on here? Look at this guy. Okay, so here's my function, x squared plus y cubed over x squared. All right, now, can you even visualize the graph? I'm not going to lie to you. Like, let's see, what happens? Y cubed, so as y gets bigger, it's going to sort of outstrip whatever x is doing. I guess I could fix y at a value and then play with x and see what z does. I could fix x at a value, play with y and see what z does. But this, we got to practice. We got to do a bunch of these and see what they look like. So, all right, so you ready? Here it is. Bam! Oh yeah, that's pretty cool. That's really cool. That's awesome. Now, let's check this thing out. Yep, so let me flip this thing up. Yeah, that's awesome. Now, notice one thing. Let's see, we're going from -1 to 1. Yeah, so here's z, here's y, right? Basically, if you look right here, it does put a little x there, doesn't it? At x equals 0. It's like, nah, this doesn't exist. Not allowed. Let's throw, what do I want to do? I want to do y max. Let's make our negatives a little bigger just because this is fun. Make our negatives just a titch bigger, and then our maxes 5, and let's go 5 again, and then graph that sucker. Yeah, see, it's giving me the same thing. It's just bigger. It smells, look at that. It smells very much like an x cubed down the middle, and then it levels off as x gets bigger, which we would expect, right? As x gets bigger and bigger and bigger, we're probably going to have this sort of, I'm not going to say asymptotic behavior because we don't have this linear behavior, but we have this cool asymptotic looking behavior in terms of it leveling off. Fun stuff. All right, well, I just wanted to show you that. I hope you enjoyed that. I think that's going to be it for now. I will meet you back here where we'll talk about level curves because level curves are awesome. See? Okay, now we're going to talk about level curves, and I love level curves because they're right in my wheelhouse in terms of projections onto an axis. They're really, really helpful. So let me give you the formal definition. Level curves of a function of 2 variables are curves. They're just curves. But the book doesn't, I don't like the way it necessarily defines it because I'm going to call this in the xy plane. xy plane with equations f of xy. Now remember, whenever I see an f of xy, just like you had to be trained, every time you saw an f of x, you thought y. Every time you see f of xy, think z, right? In that space rather than in that plane. F of xy equals z equals some constant, k, where k is in the range of z, or f of xy. All right, now remember, if we have domains, remember when we first started talking about these, we talked about domain, 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 but we also talk about range. Now, let me show you something. I'm going to build that awfully drawn hemispherical shell. So this guy is just going to be the surface area of this hemisphere, right? Now I'm going to plop that over just like this and like this. It's the same thing, and I'm going to go to this thing over and over again because it's an easy one to visualize. I'm sorry for the terrible drawing. And here's z, which of course is equal to f of xy, right? All right, now from before, we already know that its domain is down here. It's going to look circular, right? It would have to. All right, so here's my domain, right? And then it's going to look, ooh, I want to use my little thingy-dingy. Let's do this guy. Ooh, here's my domain, all right, of the circle. Oh, let me erase this, make it look pretty. Sorry, I'm OCDing out over here a little bit. All right, let's try that again. Now, let's say just for giggles that, wait, my pen's not working. All right, oh, there we go. Let's say for giggles that this sphere goes from, I don't know, let's call it from 4 to 8. So it's a hemispherical shell, right, from 4 to 8. Which means it's a hemisphere of radius 4. And we could probably build that. I mean, if you thought about how to build a sphere of radius 4 and then just move everything up, right? And then we kind of need to know a center point, et cetera, et cetera. So clearly, this is my domain, right? This guy right here is going to be my range, all right? You with me? And then I've got a bunch of points. Now, let me explain how level curves work. Well, let's say, let's see what it says first. What it says is f of xy equals z, and z equals k. So f of xy equals k. So let's just say for k equals 4. So what we're saying is f of xy equals 4. Well, do you agree that what that would be is, since this thing doesn't start until k equals 4, it would simply be the boundary line of D. It would be the outside guy. All right? Now, let's change it. See what would happen. What if we said that f of xy equaled 4.5? All right, now we're moving up here, and now I've got a slightly smaller circle around the outside of this guy, right? So it might give me a level curve, horribly drawn, just like that. I'll give you one more example. How about, let's go green. How about f of xy equals 7? Well, that would be kind of way up here, right? So now I'm just talking about this top guy, and if I project that down, that idea of projection down onto the plane is super helpful. You have no idea how helpful it's going to be down the road. I would get this little awfully drawn circle. That's it. These are the level curves. Now, the thing to remember is you can only take a snapshot of values of k of the level curves, because think about this. If you took every single level curve and put it on the xy plane, what would you get? You'd get D. Now, I'm going to do a function, and then we're going to look at it. Then we're going to look at its level curves, which is pretty freaking cool. All right, we'll look at its level curves first, and then we'll look at the function itself and kind of see how it works. It's pretty fun. All right, I'm going to do f of xy, remember, thinking z, right, is equal to sine of, let's see, what do I want to do? Let's do sine of xy. You know, what's the domain? Real quick, domain. Any problems? Can the argument in sine ever be 0? Yes. Can it be negative? Yes. Can it be huge? Yes. Can it be small? Yes. Okay, so this is all reals, but it's all reals in R2, right? Now, another way to write this, I want to show you this. This is a new notation. This is exactly the same thing as negative infinity to infinity cross negative infinity to infinity. This is a new notation. This means this. We're crossing those two, all right? Which, don't think of it as crossing vectors. This is just a notation that we use to say, okay, we're going in both directions. And then what's the range? Now, we haven't spent a whole lot of time talking about the actual range of a function of multiple variables, but what is it? Well, it's the output values which of f of x, y. It's what remember, what do? It's still just a machine, right? What do? I stick points in, and what do I get out? I get f of x, y's, right? This guy works on it. This is our function. Out pops f of x, y's, which are equal to z's, right? So the range of any function of multiple variables is equal to the set of f of x, y's such that x, y simply comes from the domain. That's all it is. It's the z values that we get. Well, we're not afraid of that, right? Sine only spits out values between -1 and 1. So the range on this guy is -1 to 1. Yeah, see how I doubled back on the range there? I think I missed that earlier, but actually I'm sure I did. Anyway, so this is it. This is what we got. I have no idea how to graph this, right? I mean, if x is 0 and y is 0, I'm good. I get 0. If x is 0 and y is something else, I still get 0, right? I mean, if I get like pi thirds and pi fourths and pi sixths, and then this guy's 1 or vice versa, I can play with that, but we're going to need a little bit more help in terms of looking at what this graph looks like. So what we're going to do is, give me a second, I'm going to cook the book so we can look at the functions, and then I'll meet you back. We'll look at the function first, and then we'll look at what the level curves look like. So I'll see you at the graphs here. All right, this is the cool part. Now what we're going to do is we're going to look at the graph of sine of x, y, okay? And I love this part. It's so much fun. Okay, so here we go. Look at that. Oh my goodness, it's crazy. Look at what I did. I set x min and y min, -3 and then 3 and 3 for their maxes. Now I want to show you something. We must agree that when z equals 0, okay, so here's z equals 0. Here's that plane that chops through. Think of it as cutting all the way around this graph. What does it look like? Well, let's take a gander at it from the top. Well, we know if x is 0 and y is 0 or y is 0, right? If either of them are 0, I know that the value of z is going to be 0, which is going to put it smack dab right down on the plane. But look at this. We're going to get all this other crazy action going on, because here's, let me give it a little better. Here, whoa, I went the wrong way, didn't I? Let's go this way. See, as z cuts around, all of these curves are going to cut in to the xy plane, which is the same thing as when z equals 0, right? So let's see how that plays out. I'm going to jump over here to Desmos. If you guys don't have Desmos, you absolutely have. Now look at that. That's awesome. All right, these are the level curves for sine of, now, I do want to point something out, but I just interrupted myself. You can't write z equals sine of xy in Desmos. It'll freak out and it'll say, I'll show you what it says. If I try and put that in, and I go z, it let me. That's crazy. Last time it did, so ignore what I just said. All right, now here's the coolest part. Watch. As I move z around, what happens? Well, the shadow, think of this as the stick figure shadow of just the contours of the graph of those points, x, y, and z. They get projected just like there was a light just on that boundary down onto the xy plane. Look at that. That's so cool. So if you think about it, if I move z up, let's move z up all the way up to 1. Okay, so there's, whoops, that's too far. I move z up to 1. Now let's go back to this, and I go, and I move this all the way up. That would be the same thing as when z is 1, right up here. This is where the curve is hitting it, and this is what it looks like. Now, again, if I ask you on an exam to draw Level curves, it's going to be extremely easy to do with the figures that or the functions that I give you. So don't panic. You do not have to do this. If we do it in class on homeworks, we're going to be able to use this graphing software. I am, as most of you are well aware, I am artistically inept. So I have a very difficult time visualizing some of these things. So again, I would not ask you guys to get too crazy. Okay? All right. Oh, I got a question. Why is at 1 are there none? Well, because at 1, it doesn't, the function z doesn't live that high. So when I cut across the plane at exactly 1, not close to 1, none of it is hitting the xy, or none of it is none of the z plane is hitting the curve, is hitting the graph. All right? I hope this was helpful. I hope it was fun. We're going to have some interesting times playing with it. So I'll talk to you soon. See you tomorrow, and let's do some mathematics.